Hello and welcome back to Crystallography for everyone. In the last video, we saw the Bravais lattices in 2 dimensions. At this point, I think we are ready to move on to 3 dimensions. This is the space in which we deal with most crystals in real life. It's where we're going to spend most of our time throughout this series, and I think we are ready to do it at this point after a thorough study in 1 and 2 dimensions. So I've brought back our trusty friend, our definition of a lattice, and we're going to see that this definition holds in 3D the same way that it holds in 1 and 2D. So I'll start off by defining just our axes here. So we've got a 3-dimensional axis. Call this direction X. We will call this direction Y. And we'll call this direction Z. And I will define a lattice on these coordinates. So I'll change colors here. I can draw my lattice translation vector, A, good old friend A, it's been with us since the first video, and I can draw our lattice translation vector B here. These vectors are still going to have some angle between them, known as alpha, and this would give us our 2D lattice. If we want to go to 3D, the same way as when we wanted to go from 1 to 2D, we're going to have to add another lattice vector. I think that you can notice a trend here. When we were in 1D, we needed one vector, one lattice vector. For 2D, we needed 2. So for 3D, I think that it's fair to say we're going to need 3. I will define this vector as C. I'll add this vector symbol down here too. So now you're probably thinking, this guy, he's terrible at drawing, but I actually drew this on purpose, not in line with the z-axis, just so that it would be clear. This vector does not have to be collinear with the z-axis. The z-axis here is just to show some reference point for our vectors. What we're actually going to do is define some more angles. So we're going to define an angle between B and C, and we're going to define an angle between A and C. I'm going to call the angle between A and C gamma, and I'm going to call the angle between B and C beta. So we have alpha as the angle between A and B, beta as the angle between B and C, and gamma as the angle between A and C. At this point, we can start decorating our lattice points. But I'm only going to show these 4. The same idea Okay, I'll show a few more. The same idea as before applies here. Our lattice points will be infinite. They will extend off into space in a periodic way, and they will each be indistinguishable from one another. So I'll draw this box in. So we'll go through the same thought experiment. We can stand on this point. Now, I can look in several different directions. The same way I could look in several different directions on the line. Now I can look down this way, change colors. I can look down this way, I can look this way, I can look over going in the minus x direction, in the plus y direction. I can look up to another point here, or out here, or out here. And all of these points are going to look the same. Once again, I have no way of determining which point is which. And that all stems from the definition of our lattice. Each point has identical surroundings and is indistinguishable from every other point. I really want to emphasize that. The same way that alpha, A, and B could take on different values to form different Bravais lattices, alpha, gamma, beta, A, B, and C can take on different values to form different types of lattices. It's convenient at this point to break up the lattices even further into crystal systems. Crystal systems, and then the Bravais lattices. In the next video, we will look at the 7 crystal systems in 3 dimensions, which give rise to 14 Bravais lattices. I hope to see you there.